We're ready to go. So go ahead, Ian. I'll let you take it away.
Okay. And Adam and I guess, are just going to kind of trade off. We didn't really rehearse, so forgive us for any wandering or being disorganized. But this is not going to try to be a talk really to introduce Kubernetes or really deeply educate about Kubernetes, because it's a big topic area, but we're going to try to give a perspective on how we got started with it and why we used it, and what we like about it once we got into it, and how we've leveraged it, and now how we probably, we are trying to use it for everything we do, because it provides certain capabilities that just once you get over the learning curve, which is significant for sure, it does provide real value, though. The learning curve, we think it's worth it. Yeah, but yeah, but so hopefully everybody knows a little about Kubernetes. It's basically, whereas Docker lets you manage containers maybe on one machine, Kubernetes is tailor-made for managing containers on a lot of machines, and sort of, managing that whole ecosystem of containers interacting with each other.
And before you switch slides, the two graphics at the bottom of this slide is a hint as to what's going to come later. The left side shows usage. The right side is a snippet of a Moqui machine that shows the bill for the usage that's in the left side graphic.
Those are seconds, but this is a bill where we're discounted because it's a
This is like a bill of 952,000 compute seconds.
So, and then the left side is a tool called Grafana, and sort of each band of color in there is an individual compute job, and it lets you see all the jobs running together over time and how much CPU they're utilizing. So, we came from OFBiz on Docker. We were early Docker adopter, and we really benefited from the sort of the discipline that you get from packaging your application as a container.
Because at the time, we loved OFBiz. It was a black box application. It just worked. And so we used it for all the customers we had. But then each one had particular requirements and alterations and changes that they needed custom to their system. So we packaged each customer's OFBiz in their own Docker image and then deployed them on the same machine. And it allowed us to isolate all that stuff without having to allocate many virtual machines for each particular customer, or, God forbid, physical hosts.
And that when you're developing, like if a customer isn't necessarily pushing updates as hard, and they've just been in an operational mode, and you have to come back to their job, that all your dependencies, are packaged as a unit. And so if you have a new job where you're adopting new, versions of libraries, and an older job that you're having to go back to those older versions of the libraries, it's super easy to switch between them, and you and everyone else you're working with on the job have consistent dependencies, and you don't get as much of this, well, it works on my machine kind of thing. So that was a big win. And we moved to Kubernetes specifically because we did a 3D rendering intensive job where we needed a lot more CPU than a single machine. We needed to harness a whole network of machines to do what we were going to do.
And I was watching Ian while he was doing watching, of course, listening to him complain about stuff. And his initial attempts were doing it by hand, where he got the request from the customer and then would set up a shell script that would run all of the render jobs in series on his desktop initially, and then started running them on a cloud machine, still one at a time. And then we played a little bit with tech time to do a little bit of scheduling of that, to give it a shell script.
Yeah.
But it was still kind of limited in how many machines it would scale to.
Well, and the problem there was, yeah, we initially did it using Jenkins, and I used the Terraform pipeline in Jenkins, and it would provision a machine to run each render and then shut it down when each render finished. So we were wasting a lot of machine time, starting and stopping machines, but sort of pointlessly. But that was just the way the Jenkins Terraform pipeline worked. And so we needed something where we could queue up all these jobs and then spin up machines to process that queue on demand, but then use the machine over and over as long as there are work items in the queue. And then as the queue gets emptied out and the work goes away, then spin the machines back down. And we looked at a number of different options. Adam spent some time with Docker Swarm.
Oh, yeah, I was trying to get Docker Swarm to run in Docker initially because I didn't have hardware at the time I could run it on. So, and this was a valid way to do it. They said, if you want to play with Docker Swarm, just set it up to run nested in Docker. So I set up a 3-node swarm in Docker. Well, then my UPS batteries decided to give up the ship. They died, and my computer rebooted, which is normal. Power loss happened. Well, the 3-node Docker Swarm just said, oh, we can't reach quorum.
Yeah, it couldn't recover.
And it couldn't recover from a power outage. And I'm looking at the swarm. I'm not looking at the code. I'm just looking at the computer going, you're pushing this as a fault-tolerant, highly scalable, recoverable system, and it can't function when all the nodes of the cluster go away? I don't trust you. Bye-bye. See you later. And I just said, we're not using Swarm.
Yeah, and there was, I can't remember now, there are other things about Swarm that just seemed not ready for prime time. And so even though Kubernetes was being on the front end of the learning curve, we were like, well, this is a lot to figure out. It just was pretty obvious that it was already kind of the dominant player. And so we just, that's what we did. And we learned how to use it enough to do what we were trying to do. So that and scaling and like auto scaling hardware, scaling processes is something that actually Kubernetes has a lot of support for, has deep support for. And that complexity, I think maybe a good way to put it is, everybody that tries to avoid using Kubernetes is going to recreate Kubernetes, like that. To get its capabilities, you end up with something complicated. And I think that was Swarm was trying to be more simple, but it just, you end up with the tools that Kubernetes has if you're trying to do the task that it does. So I think it's worth it to get the flexibility and the ability it has to create application specific zones with different hardware for different kinds of tasks, and spin those up and down independently, are very robust in Kubernetes, which is got to be a part of it coming from Google, where they knew that upside down and backwards.
I don't have too much more to say on this particular topic. We get these features for free from Kubernetes. So anytime we're doing a lot of different compute resources, it just works. And that's a benefit for us, having something that just works, because we don't have to write anything to make it work.
And so for development, we went through, I actually started on KubeAdmin or KubeADM to trying to use it to develop on my desktop. And that was kind of a painful way to start out. I did get it working, but it was not easy. And then also we still had quite a few applications that were Docker based. And so, kind of Docker and Kubernetes were, fighting over who gets to use the network card and stuff like that. And I just kept looking for something better. And that's how I came across K3S and K3D, which are from Rancher, who Rancher makes a really nice UI for managing Kubernetes. And they built a version of Kubernetes that has scaled down services targeted specifically at like your developer running Kubernetes on a low resource machine. I mean, and when I say low resource, I mean kind of in the sense of your laptop as opposed to like a giant honking server. And then K3D packages K3S as a Docker container. So you can actually run multiple Docker clusters. You can run multiple Kubernetes clusters on your laptop. And, you know, as long as your application isn't too aggressive, you can actually run 2 customer jobs at the same time and be able to bring one up and do something without taking the other one down. And that's a huge convenience. Any comments on this? You work here.
While Ian was working on Kubeadmin, I was also kind of racing him to the goal. We were both trying to figure this out at the same time, and he did win eventually. And so I kind of stopped off on some of that. One of the issues I had with Kubeadmin is it has no opinions. And so you end up having to pick all the different backend implementations like Kubernetes that you deal with, and that was too much at the time. Whereas K3S and K3D came up with simple defaults, so it just worked out of the box.
Yeah.
And then we could learn Kubernetes particular object definitions without having to deal with whole virtual drives, and virtual CPU, and virtual network, and all the other things that are just too many terms flying around.
Although, when you do get into actually running it in production, Kubeadmin actually is great, and that sort of lack of opinion does give you a whole world of options about how you deal with the network, how you deal with storage, how you deal with your compute. So that there are whole pluggable, you can completely change out how the software defined networking is defined between, say, Flannel, Metal LB, and your storage, same thing. So that there's a lot of discipline in Kubernetes for making these resources generic and pluggable. And that is also a huge advantage of Kubernetes. And I think is letting them continue to really innovate because those opinions aren't baked into the ecosystem. It lets people go, I've got a new idea for creating storage, and they can create a storage layer that can plug in. So another tool, Helm, is the kind of dominant software deployment system for Kubernetes, and it's similar to Docker, but it has way better templating, like to template the definitions. You could think of it as a Docker file where you can have, you know, decisional logic in the Docker file or in the Docker Compose. It's more like Docker Compose, but importantly, it also is hierarchical. Like you can have a Docker Compose that refers to other Docker Composes, would be the analogy. And then Helm file is a tool that sits on top of Helm, and it actually can rewrite Helm files. So you can do things like, it's like a macro processor where you can rewrite somebody else's chart even if they don't expose that functionality as an option.
Maybe as another analogy, a Helm chart is similar to a Debian package, and then Helm file is similar to a PPA.
Yeah,
there's a little bit of overlap there, where you can have repositories of packages and install all of them, and then configure their scripts to work together or separately. It's Go-centric.
It is Go-centric.
It's very Go-centric. The variable expression logic is Go templates. So, okay, you got another term to learn. There's a lot of that in the Kubernetes landscape, hence the large learning curve.
And so another capability that Helm file brings with its rewriting function is this idea of environments, where you can retailor the deployments based on the environment you're deploying in. So like you can have your local development environment and your staging environment and your production environment, and have the chart rewriting be different in each of those. So we got an example of this in the
Yes.
coming slide.
And there's a lot of heads up learning, heads up talking about the things, figuring stuff out before you get into the fun areas, code.
But I do think you make a good point with the idea, though, of Helm being like a Debian, like a Debian package. It lets you really compartmentalize your infrastructure in a way that is generic and reusable, like as components. So whereas in a Docker Compose, if you make a Docker Compose for one customer, it's got a lot of that customer stuff baked into it. Whereas if you make a Helm chart that then you can, if you break your application down into separate Helm charts, like we have a Moqui Helm chart, we have, our Postgres Helm chart, you have your mail server, each of those becomes a separate component that you can pull in and stick together, and it lets you get a lot of reuse out of that infrastructure definition.
So will you have a slide moving forward that shows how you put all these together?
Some of that, yeah. Like now, where is that though?
Keep going.
Keep going. Well, we should talk
Yeah,
about
no.
this. Yeah.
Not
actually,
to disturb your flow.
Yeah, no. And actually, the continuing on some of the just raw capabilities that Kubernetes has in contrast to Docker. So in Docker, when you define a container, say your database, that container, it starts up and you're running Postgres, but it's kind of that you have that Postgres container. You can't as easily sequence the order that they start in and tasks that happen in the process of doing that. So Kubernetes has this notion of init containers that are like containers that run before your container. So that then the actual main container doesn't know anything about. So you can do things like this slide shows that I want to fetch my backup from S3. I want to start a copy of Postgres just to load that backup. And, let's say with fsync turned off, so you make it go really fast. And then I want to start, once that all succeeds, I want to start Postgres. And then the Moqui container, meanwhile, here you finish this.
The Moqui container, that second row there, our first attempt at the Moqui chart used the pre-existing pre-built Moqui demo image. We did that on purpose so that we could, of course, not rewrite it while we were figuring out the rest of the parts we needed in Kubernetes, but it also validated that what we had was going to work in a real environment, that we didn't have our own opinions built into the Moqui image itself and treated it like a black box, like everything else we've been talking about. We just trust the software. So once we had that going, generally the Moqui demo image immediately starts Java and it goes off and tries to connect to the Postgres database. Well, in Kubernetes land, it is designed so that everything starts up at once, magic happens, and then everything works. But of course, that's not the way the real world works. Things start in parallel or there are delays, and so you've got to kind of wait a little bit for things to get settled in the system. So using the existing Moqui demo image running as a container, we had to use Helm file patches, which are coming in the next slide, to add a bash shell script effectively that fetches some variables, and then another image possibly that uses a PSQL image to then say, hey, Postgres, you ready? No, wait. Hey, Postgres, you ready? No, wait. And it would just continue looping like that. And then another image after that that synchronizes the database, does system upgrades or runs seed or whatever, does that first. Meanwhile, while all of these init containers are going, the front end knows that the Moqui pod isn't ready yet because it's in init phase. So it can put in a special web page saying, it's not ready, please wait. It's not ready, please wait. Whereas if we just immediately ran Moqui, it would say,
Errors.
it's not ready, error. It's not ready, error. So that's why init container phase is much better in Kubernetes. In Compose area or Docker area, you can't initialize containers in sequence. You can add scripts to a container using volume mounts, but you can't really add new binaries into that like you can with Kubernetes init containers. So
You have to rewrite the entry point.
you have to rewrite the entry
basically,
point inside of a regular Docker container to do this kind of
traffic-
single step
traffic control.
initialization flow.
So it's like a wait state.
It's a
Yeah.
wait, and you can do whatever you want.
But
Yeah.
without having to tamper with the upstream images. And I guess it's worth, when we're saying the original Moqui container, that if we weren't clear, Kubernetes uses Docker containers. You can use your existing Docker container, but it gives you this extra layer of control and kind of traffic control on top of it. And then, so if this, I don't know if this is going to be readable, but this is a specific example of using environment settings and switches that you pass in to change what the chart does. And this is actually an example of a patch where we're adding, Adam, why don't you explain this? I think this is your slide.
So in Helm file, one of its config files, it's YAML, but it's also more than YAML. And when it first reads the text of bytes, it interprets it as a Go template. That's first. And so you see the double curly bracket goes into the Go template syntax, and it gives you binary conditions, and you can look at variables. And this is showing that is the Postgres image going to have S3 connected to it? It is. Okay. Let's go modify the Postgres stateful set. We're going to add a temporary directory to store the S3 backup. We're then going to attach that temporary directory to the restore backup container, which already exists in this stateful set. Then we're going to add the init container before the restore init container to download the S3 files. And in here, the secrets necessary for that are in the init container only. Postgres runtime never sees the S3 access parameters. Those are a security layer violation. So you can do all this fancy stuff in the init container phase, extracting things. We've got one example to speed up developer process where we fetch the file from S3. I do a zcat, count how many bytes are in this restore file. And in the one example I had, it is 1 gig. Then I add a Postgres config snippet that sets the wall log file size to the bytes of the restore file. And then import the restore file, and Postgres never commits to anything while it's restoring this file. So it runs really fast. And then it gets done, it commits everything. And then regular Postgres just runs with normal wall size and normal commit periods. And that's only done on the developer workstations, because you'll do something programming-wise, oh, I screwed up the database. Let's go back and reset to a known working state. And so you want that flow fast. And so this lets us have the production data, which I'm getting ahead now. Production, staging, and local dev scenarios with all these different knobs that you can tweak. And it's all encoded in a concise way here.
Right, like the production deployment would deploy the live data set using credentials that the developers don't even have access to, but that the local dev environment would have different credentials to load a sanitized data set that doesn't have real data for real users in it and that sort of thing. And that you just, you don't have to go through and change all these settings locally as a developer. You can just say, I need the local dev environment. And so that's, I guess it's worth noting here that this is using then the upstream Postgres chart, doesn't change at all. Like we don't, from Bitnami, we're using their Postgres chart, and we don't have to fork or do our own local copy to add these capabilities like the S3 restore fetching. That Bitnami doesn't do that, but you can add that without having to modify their chart. And then as they continue to come out with new releases, it just plugs in. And this is a good example of different, that we're changing memory sizes, changing the number of CPUs to use based on what environment you're deploying in.
And I'm showing the same presentation on my laptop. I'm one slide ahead of you. So I'm doing this kind of like leading into the next bit of information we're going to talk about. My previous talk, or the previous slide, was showing how we can have S3 turned on or off based on some variable. Well, on the current slide, it's the second image is the local overrides. I write a file in a particular location and I can change the values that make sense for my particular work environment. And this setup is for my desktop back at home. The first slide is the defaults that we've decided upon when we just like rolled some dice and then, okay, we're going to make these be the defaults. And leading or going back to the graphic on the first slide where you saw the resource utilization, this is representing how many compute nodes could be automatically allocated and then utilized. So the default here says 24 CPUs and 30 gigs. My desktop, being a little bit smaller than the cloud, I've told it to use 4 CPUs and 4 gigs. That way I can have some space left over to run Google Chrome because it's a big, huge, fat pig. And so I wanted to limit the blender to not overrun my system. And then you also see how I've got the Postgres S3 parameters listed there, but I've got them blacked out for security purposes. In my local dev environment, I don't have access to production S3. So I've got the developer S3 access, and that's a manual process to get it from the production area to the developer area. And we've trimmed things down in that system so we can really isolate production and staging flows with various security domains.
Yeah, and I guess this is continuing.
This is a continuation, and now you're seeing there's a staging setup and a production setup. And I should have those pretty well aligned so you can do a visual compare back and forth. One of the things we're doing when we're comparing files is I'll have 2 windows side by side and do a virtual window switch to see, okay, are they the same thing? They're the same thing. Where's the visual differences? So it's a technique I have for trying to find changes. And in this file here, it's not only the resources that are different, but the actual branch that gets checked out to run Terraform machine allocations. So we can have a staging or production machine that gets completely rebuilt by just changing these variables here. We don't have to go edit a whole bunch of files every time we do that.
I guess if anybody has any questions, I guess we can save questions till the end. So another interesting thing we've used under Kubernetes is the Terraform operator. Operators are sort of these containers that are long-lived containers that manage a process for you in your cluster. And this lets you, the Terraform operator lets you do GitOps kind of things where you define your machine environment using Terraform. And then as you change as you change your definition, your Terraform files actually define the infrastructure that then this Terraform is always, this operator is always watching. And when your definitions change, it will manipulate your runtime environment, your actual compute infrastructure, to update it based on the definitions in those Terraform files. So it really gets you into that your software, that your whole operational infrastructure is kind of this software artifact that is being updated in real time by this operator. I don't know if that adequately, there's a lot going on here. I don't know how many people have used Terraform. Do we have many Terraform users? I don't know in the audience. Do you guys use Terraform here? Oh, you like Terraform?
No.
We've spectated its usage.
Yeah. It,
We used it a long time ago, but then it wasn't the same.
Yeah.
The Alchemy team uses the Terraform in some capacity.
we are big fans at this point because it's complicated to get it set up, but man, like if you have everything done as turnkey terraforms and you need to stand up another environment, it's, you just say, do it, and everything, DNS, everything gets stood up automatically. It really does deliver the promise of being able to define your computing environment as a software artifact and then enforce it from that definition, or to produce it from that definition.
It can bring up our 3D rendering app in 15 minutes.
That hands off too, and that it's restoring stuff and restoring the database dump and it's doing everything. So then some of the other infrastructure you get, there's robust logging system called FluentD that can take all of your logs coming from all of these containers running in your cluster and load them up into a Elasticsearch enabled web environment where you can kind of, I guess, like Splunk or something like that, where you can then very rapidly search all your logs for information and match patterns. And so that's a really powerful tool.
And the way FluentD works is it uses a feature of Kubernetes called a daemon set. So FluentD or Kubernetes has decided it needs more resources. So somehow magically a node or more nodes have shown up. Well, a node is a virtual machine or physical computer. And Kubernetes uses a thing called the daemon set. So every time a node comes in, it goes, I'm going to run a system process on that node. And it grants special permissions to those containers that are running, so it can mount the host file system. It can look in var log, look at all the containers, and add listeners, so that every time a container starts up, FluentD goes, oh, okay, give me the data. And so all of your nodes across the system are running a FluentD pod, and that's automatic with a daemon set. Then FluentD has pluggable receivers, and out of the box, it recommends using Elasticsearch. Brief aside, that's currently being changed quite a bit upstream. The whole OpenSearch Elasticsearch kind of split is been going on. So this application, it was Elasticsearch, and so that's what we're demoing here. The screenshot you see is a very small window into the Terraform machine allocation that happened on staging a couple of days ago, where it had called Terraform called Amazon, and you see the very end where the very first line says the machine's not running yet. And then Terraform operator comes in and goes, okay, I've allocated the machine, it's now talking back to Kubernetes. And then our logic picks up and goes, oh, it is running now. I have accepted that it's running. And the second column of that is the Kubernetes pod name. And that's the benefit of FluentD and Elasticsearch, that all these pods are running in parallel. And they're all outputting their logs and their events separately. And you get a unified streamed view of these based on a time component.
That's searchable.
That's searchable. And the Moqui community is familiar with Elasticsearch, and there's a Kibana tool that talks to Elasticsearch and gets you access to all the fancy parameters. So it's really FluentD that's new to the Moqui side.
And so another tool we've used is Istio, which is what they call a service mesh, and it lets you control not only ingress traffic, or like traffic ingress and egress traffic coming in and out of the nodes or the cluster in the case of Istio, but even all communication, if you want, between every container in the system. So you can create security rules and enforce security rules about what can talk to what and under what conditions. And it knows how to talk to OpenID. So here, if you try to talk to Moqui, coming into the cluster and your connection doesn't have an authorization yet, you're going to get bounced to Keycloak, and you don't even get an opportunity to talk to those network services yet. And you're going to go through OpenAuth or OAuth and get authenticated before you can even talk to a service. And that's a really cool capability too. So
one of the things not represented in this graph, from here, it looks like Istio is only intercepting external traffic to your backend sources. It can actually intercept sources or communication between backends. And if you've fully implemented the HTTP header forwarding that's available, every external request that hits Istio gets a particular ID added to that particular request. The backends can take that header, and when they talk to the next level backend, they forward that ID along with it. If Istio has been configured to do, blue-green deployments, or you're rolling out a new backend version, it can know that at all levels of communication and make certain that version 2 of Postgres and version 2 of Moqui and version 2 of Keycloak are all kind of being forwarded along the same path. We haven't deployed that yet, but it's in the documentation. And we are only discussing in detail things we've done, because that's a more truthful scenario.
Right.
yeah, but I think that's a very Istio can route your connections actually based on OAuth grants, and those OAuth grants could even, we've been working on hooking Keycloak and Moqui together so that, for instance, if you get a party classification, that turns into an OAuth grant in Keycloak, and you could do like beta user, and that the beta user's requests get routed to, you could have your next revision of your app deployed simultaneously. You could have two Moquis talking to the same database, for instance. You'd have to do obviously some cache clearing tricks there, but that you could say these users get the new version and all the other traffic passes through. So that's like the ability to have this fine-grained deployment is really powerful. Now there is overhead, as much as like 30%, but the talks you have around Istio, what the consensus is like the ease of the developer experience of being able to work this way justifies the additional cost. Another tool we've used is Tecton, which is a batch processor, and but it runs each step in the batch process. Each one is a separate container. So you could think of it as like if Docker Compose files ran in series instead of in parallel. Like in a Docker Compose, you're saying service, if you got 5 services in your Docker Compose, they all start up and they're all running at the same time. In Tecton, you can say, I want to run this Red Hat image that does this thing to fetch some data, and then I want to run this Debian image that's going to do something with the data. It lets you define completely separate container environments in steps working together, and that they can share storage and other resources between the steps. And we use this is what we use to manage the 3D rendering process. And it's a really powerful tool. And because everything, each one of these is a full-fledged Kubernetes pod running in series.
Well, Tecton actually adds a few more definitions into that. The unexpanded boxes are what are called tasks. Then underneath the task is called a step. And they are all run in sequence most of the time. There are some ways to run tasks in parallel. There's a loop capability. So you could have those like expand and run 50 tasks all at once. Each task gets dispatched to Kubernetes. Kubernetes then makes its various hardware allocation decisions to deploy it on nodes, which could be expanded. So it's all the same thing over and over and over again. Tecton gives you a little bit more variable control over these things. Tecton's used a lot in CI/CD, and it has relationships with Jenkins.
Yep.
If,
Jenkins
so
X.
there's some back and forth between who gets to write the various things in those communities. So Tecton is a Kubernetes aspect, and we're using Tecton directly, not via Jenkins X. Before you go
Yeah.
back to that slide, if you read the text, this is a Blender little thing, and that's part of our 3D rendering application. And this particular Tecton task is where someone has uploaded a file, and we're trying to figure out what the file can do by calling Blender and saying, hey, give me the stuff. And in this snapshot, we had a syntax error in our shell script, and we weren't quoting our variables. And so that's what that particular error message means. We could have found that via the FluentD aspect too, because it grabs the same logs, but we're showing in this interface because it's a little bit prettier than the FluentD interface. All right. This here, we had this screenshot on our introductory slide, and it is a view of one of the Moqui backend screens. Actually, let's flip back to the previous slide briefly. The Probit task, we expanded this. There are two containers running in the Probit task. One is start time entry, one is finish time entry. The initial definition for this only had the Probit task, which ran Blender. Well, got all that working, needed to figure out how to do billing. So now we used Helm file patches to add automatically hooks around every single part of the Tecton process that needs to have its time recorded. And these, the start time entry and finish time entry, take the current task type, do a RESTful call back to Moqui. Moqui then records that in its database. Now flip forward to the next slide. We're getting close. We're getting close. In this next slide, we then have a batch process that runs at midnight, takes up all of the computes that were run during that 24-hour window. And in the lower right, it shows that in that 24-hour segment, there were 952,000 compute seconds. If you do a little bit of calculator magic, that's 11 days for a single computer to do the work that was represented here. Well, this is a batch process running every 24 hours. How did you do 11 days of work in 24 hours? You don't. But that's because Kubernetes had figured out it could allocate and run these things in parallel. And 40 days, or sorry, not 40, 40 computers could do that much work in 6.6 hours. Not represented here, there's a second order that ran the next day, because this actually spanned over midnight, and it was 550,000 seconds of additional compute to finish up the job. And now we get back to the Grafana graph that shows that particular job running on Kubernetes. And the customer had started this request, and then they were confused because it wasn't processing yet. So they called us. We started monitoring it, and it was actually doing what it was supposed to, but they just submitted a whole bunch of work. And so it wasn't going fast enough yet. This particular request had 2,000 renders that needed to get done. And we had configured the system to only allocate 10 nodes. And so that's what you see at the beginning of the graph. So we logged in and we reconfigured things, bumped it up to 40, and you see it slowly increase with a little bit of a ramp. And then it continued on and worked its butt off. Each color wave through here is a pod of a Tecton pipeline. And so it's all doing all these things in parallel. It's downloading the file, it's doing a Blender render of that, then it goes and chops that render up into tiles, and then it uploads it back to S3. So each one of those little color pieces is a process in Kubernetes. And Kubernetes grabs all that stuff from Prometheus, Grafana displays it. We really like Grafana. Colors are really nice.
And I guess we may need to hurry along here. Yeah, we kind of covered all this. But so this is actually, we think, a really potentially interesting place that Moqui could play a role in the, open source universe. Is there are already this KubeCost and OpenCost APIs for tracking cluster utilization. But, what are you going to load this data into? Well, Moqui might be a really good choice for that. So that then you could bill your customers or bill your departments, internal departments. And this could maybe be like a channel marketing opportunity for us to get into a lot of existing Kubernetes installations.
Cloud in a box.
Cloud bill, yeah, internal cloud billing. So that's QA. I guess real quick, I'm going to show what this application, I guess, looks like.
Yes, this is exactly what I've been waiting for.
Some of the people on the community calls have seen this before, which goes back to what Michael said, that we talk about a lot of things on those calls and show off what we're working on. Or
so, for instance, so this is the actual site. This is a WordPress. The marketing site is WordPress, but then when you log in, this is Keycloak, like we were talking about.
Yeah.
And then if I sign in, but the let me get this meat thing up. That though, like for instance, if I go look at my invoices, that all of this is coming from, this is all driven from Moqui. Like all this business data is driven out of Moqui.
What is is this still WordPress on the device?
This is React here. And so this kind of the brochure stuff is WordPress, but actually then we stub in this React menu bar. So even though this is WordPress, this is React. And then like when you get into your project browser, this is all React here. And let me go back to that.
So in essence, like you enroll, you create an account, and you submit files to be rendered.
Mm-hmm. You attach your Dropbox or your Google Drive, and you can pick your blend files out of that and generate rendering.
And then you
uploads files to our server.
Okay.
We have remote storage, and we can currently support Dropbox and Google Drive.
Okay, and then you bill eventually you build the compute time you use to render the model. Okay.
And then the way we, so the function is to let you visualize different options, construction options. And, like the floor finish here, I can change to like a dark floor finish, and that you have these panoramic views. That this is not like a super high resolution. Yeah.
And that's what's great about this. You preferred one way, you preferred another way. Our system renders all the different ways, so then you can flip back and forth when you're trying to sell this arrangement to the customer.
And in the back end, you have the Kubernetes cluster that does not have any resources when the system is idle.
Yeah,
and then you spin up resources on demand.
Yep.
Okay, cool.
Yeah, and so
that's good.
And Moqui is a piece of that puzzle, but not the main part of the application. The main part is the blenders that are running.
And so, I can control these.
Not even that. That's just a tool to help us visualize.
So how do you like, what's the trigger? I know the trigger is from the website when you actually upload the project, but what happens behind the scenes? Like after you upload the project, what's the sequence of provisioning the Kubernetes resources?
Is
that initiated from Moqui or?
Okay. You click the buttons in the front end website. you've selected a file, you've configured all the things, you go
Submit.
poke, and you go start render.
Yeah.
That then talks to Moqui. We create a series of work efforts for every single
Resource.
render combination, and we set their statuses to begin, and I can't remember the exact term. Then Moqui now talks to Kubernetes and creates all the tectons for the 2,000 requests.
Talks to Tecton.
So Kubernetes tecton, they're kind of a similar thing. It's all running in the Kubernetes database. Tecton then goes and does nothing because there's no cloud resources yet. The Terraform part goes, oh, I've got things that need to be processed. It spins up a node. The node does its work to get itself configured, talks back to Kubernetes. Kubernetes then schedules the tecton onto the node. The first part of the tecton process now talks back to Kubernetes and says, okay, I have begun.
Okay.
So
So the step between Moqui talking to Kubernetes / Tecton, is that via the Kubernetes APIs or Tecton APIs, or how is that step completed?
Tecton API. So Moqui talks to the Tecton API and says, start render job, start render job, start render job. And then we have an external process that is watching, external pod that's watching the backlog of pending jobs that need to be finished. And based on that says, okay, Terraform, start ramping up servers. And then once the backlog clears out, it goes, okay, any jobs waiting to be done? Nope. Okay, start shutting equipment back down.
Okay.
some things I'd like to mention while we're in that question. The very first attempt at the Moqui Talk to Tecton flow was being done on the developer workstation. And since the developer workstation only had limited resources, I configured the project at the time to only do one camera and no options. So it was just a single render. Everything worked great. Well, then we sent it over to staging and it had full cloud access. And so somebody decided to test the system and upload a large file with a lot of cameras and a lot of options. And I got a transaction timeout. By default,
Is he the somebody?
well, it could have been that somebody. Well, there's a 2-minute transaction timeout, and my initial logic tried to talk to Tecton in a single transaction for all of the render requests that we had going on.
Oh, right.
And of course, it fell over. And so now we had Tectons running, but the Moqui status of that, the work efforts didn't exist. So in that particular case, is I had to implement a back and forth
recovery
of a
mechanism.
job, and each call out to Tecton ran in an isolated transaction. And I did it in lockstep fashion. So there's one job that continues to run to drain the work efforts out of Moqui back into Tecton. And it goes start transaction, set the work effort status. Okay, I'm going to start talking to Tecton. It talks to Tecton. Tecton then gives me an ID back, and then I set the status in Moqui again, and then I finish the transaction. And when it ended up taking like 30 minutes or so to get Tecton to accept all these things, depending on load. So there's a lot of that where initially you do it all in a single transaction because it's easy, but then eventually you have to go, no, I got to manage the transaction myself. Just because I'm talking to an external resource that I'm.
So finally, is it, are you using AWS as the infrastructure?
Yeah, here we are, but the we also do it on our desktop, and that also we could run it in Hetzner. And I guess that's like another interesting thing about centering on Kubernetes is that you become
Right.
relatively
It's cloud agnostic,
cloud
so to speak.
agnostic. Yeah.
But in production, are you using like EKS, or are you hosting Kubernetes yourself?
We host Kubernetes ourselves.
Okay.
The mainly the well, lock in,
Well, that's
and
the big part.
it's kind of like they just charge you a premium on EC2, like for
Well, EKS has a premium on top of EC2.
that's what I mean. And so
Yeah.
like it was cheaper for us to just run, and since we already had it running, we were like, what's the advantage? I don't know.
Right. Great. So I asked.
This image on the screen is Blender, right?
This is Blender rendered in.
So Blender is running in the browser.
No. Yeah.
No,
yeah.
this is a tool called Penelope.
Yeah.
That is doing a graduated fetch of tiles that came off of the Blender static image.
It actually makes a spherical grid and does like progressive, like what the way progressive JPEG works. So like as you zoom in, if you do a very high
On
resolution
demand.
render, you can keep zooming in, and that's one reason it loads. Like you notice when I'm switching options that it loads really quick. Like like when I change these tablecloths or whatever, it loads pretty much immediately. And that's because like it's not actually loading that full resolution. It's actually only loading the part of the scene that you're looking at and only at the level you've zoomed into.
Yeah,
So,
but by the way, the browser animation is super smooth. It's just that on Google Meets, it's the frame rate is not super cool.
yeah, let me here I can this is public. So yeah, it works well on phones too. So like you can hit this even on your phone.
It uses the gravity sensor on the phone to do the standard. You can turn around and fall into your chair.
So if people want to hit this locally, you can take a peek.
Great presentation.
Yeah,
Yeah,
very good for sure.
And simulated over there.
I asked a lot of questions because I am doing something. It's similar probably to the architecture, but not, of course, not the use case. Like we don't have anything to do with rendering and graphics. But there are some major differences, which is we don't spin up resources on demand. I mean, we do spin them up on demand, but not for a limited time period. Like once you spin up a resource, it's going to stay for a long time. So we don't have to worry about like monitoring the resources as they get spun up. So what I will be researching in the very near future is the instruction from Moqui to Kubernetes to spin up the resources. That's why I asked specifically about it. Now, I've already basically established the first way I would like to attempt it, which is directly interfacing with the API, the Kubernetes APIs. So I'm going to give that a try first, but I wrote down Tecton just in case that does not work.
And Terraform too is really great. I mean, because
We used Terraform because we had already used it to start up Kubernetes to begin with. Kubernetes has another thing called Cloud Autoscale that talks directly to the APIs, not via Terraform. But at the beginning, we were learning so many new things that we decided to stick with Terraform because we'd already learned that before in the Jenkins era. So we decided to limit the scope of the project.
well, and I think it's worth like autoscaler is great for if you have a single cluster that you want to scale the resources that it's running on, but it doesn't do all the other stuff that Terraform does, where if you're like trying to say you have a whole stack of things like CloudFront and DNS entries and a bunch of other things that whenever you create a customer account or something, you need to provision all those things, that Terraform let you soup to nuts, just do all that stuff.
Interesting.
Thank you very much. That was a very informative.
One more thing I would like to mention, just to back slightly. When Ian logged into the front-end web app, you briefly saw the key cloak screen, briefly.
Right.
Well, we do push that through the entire system. The front end logs into key cloak, it has a token. When the front end talks to Moqui, the token gets passed to it. It's looking at the JWT parameters. When Moqui then talks to Tecton, that same token is passed to Tecton. Tecton is an elevated permission model. So now Tecton says, okay, I'm taking the simple permission model in the front end token. I have to increase my permission because the file download that's coming from Drive needs a little bit more access. So it goes and Tecton gets a higher permission from its token. It then talks back to Moqui, gets the storage token parameter, which you can't access from the front end. Tecton then talks to Dropbox and gets an offline storage that it has to remember for days sometimes, because these jobs take a long time. Again, more token stuff.
Mm.
And then eventually, when the Tecton processes talk back to Moqui, the same token comes around, and Moqui goes, I know what the user ID is, and that you access just your project. So it's fully JWT token integrated across the board.
Right.
One really cool side effect we get out of using that Keycloak thing is Keycloak supports user impersonation for
Right,
administrators. And so that's really nice. Like you can, does it? Yeah. I haven't used it on Moqui. It does do it? Yeah.
Yes, sir. Log in as
Oh.
permission under the admin advanced.
Oh.
But
User
now
group.
that we've got the external SSO, it gets passed down to all the other different layers that have already been integrated with the token stuff. Some people are hungry.
Yeah, yeah, yeah. The login as thing is fairly recent. Well, why don't we close this this session? Maybe yeah, I'll stop the recording. Well, thanks, Ian and Adam. That was gave a good like overview of all these tools and how they fit together and such. Yeah, it's really good.
Thank you.